In our last module, we have discussed sequences and their convergences. In this module, we start with some applications of sequences in statistical problems. We start with the famous envelope problem and derive the limit using the results of convergence of sequences. Then we shall consider difference equations of first order and give an ingenious method to solve them, for the limiting value using the concepts of sequences and their convergences. And then we pass on to our next topic, which is known as series. We shall discuss series and enumerate the concepts of convergence of series, and finally give some examples on series and investigate their convergences. So the objective for this module is to get some applications of sequences in statistics, provide some tests for series, and also enumerate some examples of series. So let us start with one statistical application of sequence. So this is related to the so-called problem of envelopes. Suppose n marked letters are to be placed to marked n envelopes at random. Then the probability that no letters are placed in the right envelope can be expressed as Pn, which equals 1 by 2 factorial minus 1 by 3 factorial up to minus 1 to the power n divided by n factorial. Suppose the interest is to obtain the limiting probability for this problem. Now, from the convergence of E series, it is known that e to the power minus 1 has the expression summation I from 0 to infinity minus 1 to the power I divided by I factorial. Thus, we observe that Pn is nothing but the nth partial sum of the series represented by e to the power minus 1. Then, from the convergence of series, it is easy to observe that Pn tends to e to the power minus 1 as n tends to infinity. In fact, we have defined convergence of series, and we have seen that partial sums of a series can converge to mostly they converge to the actual limit. So our next application is related to recursion relations of different types. In classical probability theory, we often encounter recursion relations of different orders. And in such cases, either an exact solution is needed, or an asymptotic or a limiting solution is needed at least. So now we shall give an example or say one method of determining the limiting probability from a recursion relation without deriving the exact form of the equation. So consider the relation Pn equal to alpha Pn minus 1 plus beta, where Pn is a probability. Since Pn is a probability, we must have 0 less than equal to Pn less than equal to 1 for every n greater than equal to 1. Thus, we at once have the inequality 0 less than equal to limit inferior of Pn less than equal to limit superior of Pn less than equal to 1. And since Pn is a bounded sequence, limit inferior and limit superior are both finite and they exist. Now assume alpha less than 1. Then from the recursion relation using the properties, we get the following inequalities. The number one inequality is limit inferior of Pn greater than equal to beta by 1 minus alpha, and limit superior of Pn is less than equal to beta by 1 minus alpha. Now combining these two, we get limit inferior of Pn greater than equal to limit superior of Pn. Again, from the definition of limit superior and limit inferior, we always have for any sequence limit inferior of Pn less than equal to limit superior of Pn, and hence comparing with that obtained from the recurrence relation, we find that limit inferior of Pn is nothing but limit superior of Pn. Thus, from the properties of limits, the limit exists. That is, limit of Pn belongs to 0, 1 and is finite and is simply beta by 1 minus alpha. This limiting value can be obtained from the recursion relation using the fact that limit exists. However, since Pn is a probability, so Pn must lie between 0 and 1, and in order to satisfy that Pn lying between 0 and 1, we must have beta belonging to 0, 1 and alpha belonging to minus beta up to 1 minus beta. Thus, always alpha belonging to minus 1 to plus 1, and hence we need not to consider other possibilities for alpha. Consider next example. Consider the relation Pn equal to alpha n Pn minus 1 plus beta n, where alpha n and beta n are such that limit of alpha n equal to alpha and limit of beta n equal to beta, and they are all finite. Again, since Pn is a probability, we must have 0 less than equal to Pn less than equal to 1 for every n. Then, as earlier, we have 0 less than equal to limit inferior of Pn less than equal to limit superior of Pn less than equal to 1. Now, proceeding as earlier and using the fact that limits of alpha n and beta n are finite, we get that the limit for Pn exists in this case also and is given by the same beta by 1 minus alpha as before. Next, we pass on to our next topic, which is related to series and tests for convergences. So, we have already seen the importance of series and their convergence in the theory of probability. However, most of the convergence is discussed from first principle, but use of the first principle to check convergence for every series is not straightforward. Actually, here first principle means calculating the partial sums and then to check the convergence of the sequence of partial sums for possible convergence. And as usual, investigating the convergence of the sequence of partial sums is not always straightforward, and hence we need some simpler conditions. In practice, we often use some sufficient conditions which are commonly known as tests for convergence. So, we start with series with non-negative terms. So, let us first introduce a general result which is valid for every non-negative series. Actually, a series with non-negative terms is convergent if and only if the sequence of partial sums is bounded above. Next, we consider as an example the P series. So, consider the series summation n to the power minus p, where p is any real number. Since the series is non-decreasing and 2 to the power n minus 1 greater than equal to n for every n greater than equal to 1. Actually, it is observed that this n to the power, that this P series is a if we consider the partial sums, we find that the partial sums are non-decreasing, and one can easily prove the inequality that 2 to the power n minus 1 greater than equal to 1, and this can be proved by expanding 1 plus 1 whole to the power n minus 1 in binomial series, and then omitting the unimportant terms. And since the series, the partial sums for the series are non-decreasing, we find that Sn, that is summation up to n terms, less than S 2 to the power n minus 1, that is the summation of the series up to 2 to the power n minus 1 terms, is less than 2 to the power p minus 1 divided by 2 to the power p minus 1 minus 1 whenever p greater than 1. And as usual, Sn is defined as the nth partial sum of the series. Thus, we get that the P series converges only when p greater than 1. That is, we get the sequence of partial sums which is bounded above for p greater than 1, and hence applying the above result, we get that the P series converges only when p exceeds 1. So, Now let us give some possible observations. First one is, if summation an is a convergent series with positive terms and an is a monotonic decreasing sequence, then necessarily limit of n multiplied by an equal to 0. For an example, consider the P series with 0 less than p less than 1, then an, that is 1 by n to the power p, is decreasing in n, but n is n to the power 1 minus p, which does not tend to 0. Hence, the series diverges for 0 less than p less than 1. That is, the above fact, that is limit of n multiplied by an equal to 0, gives an alternative to check whether a series is convergent or not. So let us pass on to our next observation. Suppose summation an converges to some real number a, then an tends to 0. Actually, the proof is very simple. It can be proved using the definition of partial sums and an. Actually, one can express an as Sn minus Sn minus 1, where Sn is the nth partial sum, and since the series converges, then Sn also tends to a and Sn minus 1 also tends to a. So therefore, we get the limit of an as 0. Thus, if for some series we find that the nth term does not converge to 0, then the concerned series must diverge. For example, again consider the P series with p less than equal to 0. Then an greater than equal to 1 for every n. Since an does not tend to 0, the series does not converge for p less than equal to 0. However, the converse is not always true. The harmonic series we have defined as earlier diverges, but its nth term converges to 0. So we must be very cautious while applying these indirect procedures of checking convergence. So next, let us consider another useful test for convergence. This is known as comparison test. So first we shall discuss test for convergence. Suppose summation an and summation bn are two series with positive terms and the latter is known to be convergent. If 0 less than equal to an less than equal to k times bn for all sufficiently large n and positive constant k, then the series with an is also convergent. So next, consider the corresponding test for divergence. Again, suppose summation an and summation bn are two series with positive terms and the latter is known to diverge to plus infinity. If an greater than equal to kbn greater than equal to 0 for all sufficiently large n and positive constant k, then summation an also diverges to plus infinity. We can use some limit form for the comparison test. For this, let us consider first test for convergence. If summation an and summation bn are two series with positive terms and the latter is known to be convergent, if mu equal to limit superior of an divided by bn is positive and finite, then summation an is also convergent. Next, we shall discuss test for divergence. Suppose summation an and summation bn are two series with positive terms and the latter is known to be divergent. If lambda equal to limit inferior of an by bn, which is positive and finite, then summation an diverges. Next, we shall discuss two important tests which are known as root test and ratio test. So let us start with Cauchy's root test. If summation an is a series with positive terms and limit superior of n equal to r, then the series summation an converges if r less than 1 and diverges if r greater than 1. However, the test is inconclusive if r equal to 1. Next, we shall discuss D'Alembert's ratio test. suppose summation n is a series with positive terms, then limit superior of n plus 1 divided by n is less than 1 implies convergence of summation n, and limit inferior of n plus 1 divided by n greater than 1 implies divergence of summation n. Let us quickly enumerate some other procedures, some other tests. The first one is known as a limit comparison test. If summation n and summation bn are two series with positive terms, and limit of n by bn is defined as L, which is 0 and belonging to is just greater than 0, then summation n and summation bn converge or diverge together. However, L is assumed to be finite in this case. However, if L equal to 0, then convergence of summation So next we shall discuss some other tests. The first one is limit comparison test. If summation n and summation bn are two series with positive terms and limit of n by bn equal to L, and L is assumed to be positive and finite, then summation n and summation bn converge or diverge together. However, if L equal to 0, then convergence of summation n implies that of summation bn. Again, if we assume that L is plus infinity, then divergence of summation bn implies that of summation of n. And lastly, we shall discuss one test for alternating series. So far we have discussed tests for series with non-negative terms, and now for the first time we shall discuss a test for with terms containing positive and negative terms also. So this is known as Leibniz test. Suppose n greater than equal to n plus 1 greater than equal to 0 for every n greater than equal to 1, and n tends to 0 as n tends to infinity, then the alternating series minus 1 to the power n an converges. Next we quickly discuss Cauchy condensation test. If an is a monotone decreasing sequence of positive real numbers and b is any positive integer exceeding unity, then the series summation an and summation bn a in the suffix b to the power n converges or diverges together. Next, our next test is Rabe's test, where we assume that summation an equal to is a series with positive terms, and L is defined as limit n multiplied by 1 minus an plus 1 by an, then the series converges if L exceeds 1 and diverges if L is less than 1. So let us consider some examples. In our example 1, we have considered the series summation n from 1 to infinity 1 by 2n plus 1. As it is very easy that here we define n equal to 2n plus 1 to the power minus 1 and bn as 1 by n. Then the series 1 by n, summation 1 by n is known to be divergent, and now limit inferior of n by bn equal to half, which is positive, and hence by comparison test of divergence the series diverges. Consider our next example, where we have considered a series with nth term as 7n square plus 5 to the power minus 1. Now looking at the form of 7n square plus 5 to the power minus 1, we set bn as 1 by n square. Then the series summation bn is known to be convergent, and we find that limit superior of n divided by bn equal to 1 by 7, which is positive, and hence by comparison test of convergence the series converges. Consider our next example. Consider the series with nth term as n to the power minus n. and it is known that for any n greater than equal to 2, n to the power n is greater than equal to 2 to the power n. Now define an as n to the power minus n and bn as 2 to the power minus n. Then an by bn less than equal to 1 for every n greater than equal to 2, and since summation bn is convergent, we get from the equivalent form of the comparison test of convergence that summation n also converges. So we have just seen how sequences are necessary in statistical applications. We have seen some properties of sequences and given some statistical applications mostly in the system of difference equations. We also discussed series and their convergences and provided some numerical examples. However, there are some other types of convergences or some other types of concepts in limits. These are commonly known as big O and small o notations, and there are also sequence of functions and their convergences. So in our next module we shall discuss all these things in details.